All right, we're working through the back page of the Chapter 8 review worksheet. So number 7, we're trying to find the indefinite integral of 1 over square root of 25 minus x squared. This is another trig substitution problem where we see this is in the form of square root of a squared minus u squared in the denominator. So that matches up with the arc sine rule. So if we just use the arc sine rule, the rule is the indefinite integral is going to be arc sine of u over a plus c, and if we match our problem with the rule that we have, our a will be 5, our u will be x. So simple, easy fit there. So arc sine of u over a, arc sine of x over 5 plus c. All right, 8.5 here, dealing with partial fractions. We're starting off with integral of 1 over 4x squared minus 9. And we see that u substitution is not going to work. We're not going to be able to expand our problem. But if we look at 4x squared minus 9, we see difference of squares. So if we factor this, we get 2x plus 3, 2x minus 3. And if we want to split denominators up into separate fractions, we have to go through partial fraction. So we'll think of this as a over 2x plus 3 plus b over 2x minus 3. So we have linear factors. So if we have linear factors, let's identify the factors of each expression, and then we'll go through the cover-up method. So 2x plus 3, the factor there, solve for x, was negative 3 halves. The factor of 2x minus 3, if we solve for x, is positive 3 halves. So if we want to figure out what the a value is, we're going to cover up the 2x plus 3, and then we're going to plug negative 3 halves into the remaining x. So negative 3 halves gets plugged in to the remaining x, and then if we work that through, we'll be left with 1 over negative 6, so therefore a is negative 1/6. So that's the first portion. The factor for 2x minus 3 is positive 3 halves, so we're going to go back to our original expression, and we're going to cover up the 2x minus 3, and we'll plug 3 halves into the remaining expression. So 3 halves plugs in for x, we get 3 plus 3 is 6 in the denominator, so 1/6 will be the b value. So now we have an easier time to figure out what is the appropriate rule for each of these portions to find the antiderivative. So here, if we go through u substitution, we let the u value be 2x plus 3. du over dx is 2. dx equals du over 2. So we're left with a coefficient of 1/2. 1/2 times negative 1/6 is negative 1/12. So negative 1/12 integral of 1 over u will be negative 1/12 natural log of u plus c. And then here, same idea, our u value is 2x minus 3, will also produce a coefficient of 1/2. 1/2 times 1/6 is also 1/12. So 1/12 integral of 1 over u will be 1/12 natural log of u plus c. And we can factor out 1/12 out, and then we can leave it in this form, or we can simplify a little bit further, because we see that if we rearrange the positive term followed by a negative term, we have natural log of a minus natural log of b, which can be going through quotient property. We can rewrite it as one natural log expression, natural log of a over b. So a is 2x minus 3, b is 2x plus 3. So natural log of 2x minus 3 over 2x plus 3 under absolute value bars, 1/12 outside, and then plus c. All right, 9 and 10, these are further problems dealing with partial fraction. But we always look to see, can we expand or use substitution method. So if we look at this form here, looks like we're not going to be able to go through use substitution to match up nicely between numerator and denominator. So let's see what we can do here. In the denominator, we can factor out x squared, so x squared times x plus 1. Now, if we want to do partial fraction, we have to notice what form this is in. This is a repeated linear factor with another linear factor. So if we have a repeated linear factor, we have to take care of all the portions. So one portion is just going to be x, and then will be x squared, and then the other factor is x plus 1. So we'll have a, b, and c. Okay. All right, so this we're not going to be able to go through the cover-up method. So maybe the easiest way to go through this problem is to think of it as finding common denominators and multiplying this equation through with that common factor. with that common denominator. So the common denominator is going to be x squared times x plus 1. So if I multiply everything through by the x squared times x plus 1, we're left with, if I multiply everything through by x squared x plus 1, the first fraction, the entire denominator will cancel out, leaving us with just 4x squared plus 2x minus 1. If I multiply this fraction through with x squared times x plus 1, I'm left with x times x plus 1 times a. If I multiply this second fraction with the entire x squared x plus 1, I'm left with x plus 1. If I multiply this third fraction by x squared x plus 1, I'm left with just x squared. So now we want to identify convenient x values that will allow us to, in turn, step by step solve for each of the x's, or each of the a, b, and c's. So let's start off with the easiest one. If x is 0, that will take out this a will take out the b value, and the c value, because the x will go to 0, x will go to 0. It'll just be the b value left. So b is equal to -1, because if I replace each of the x's with zeros, I'm left with just b equals -1. So once I know what the b value is, I can update my equation. My b value here is now -1. So I'll replace all the b values with -1. And then let's see what happens when I plug in -1 in for x. If I plug a -1 in for x, it'll take out this term and this term, which will just leave me with c times 1 is equal to, and the left side will give me 4 minus 3. So 4 minus 3 will be 1, so c is equal to 1. Okay. All right, so I have my b value, I have my c value. Another convenient is using x equals 1. So if I plug x in for 1 for all the x's, and then I can also replace my c and my b value. So if I replace everything that needs to be replaced, I can then solve for a. And I get 5 is equal to 2a minus 1. And then so a is equal to 3. So once I have my a, b, and c values, I can now take the integral of this problem, replace a, b, and c with what we just found. So 3, -1, and 1. Now this problem becomes a lot more manageable, a lot easier, because this first would just be a natural log problem. The second, here, if I bring up the x as x to the -2 in the numerator, it becomes a power rule problem. And then the third one is a natural log problem. And then we have the plus c as well. All right, number 10. Notice we have x squared minus x over minus x plus 9 all over x squared plus 9 quantity squared. Now notice that this, first off, we can't expand. U substitution is not going to quite work out for us. So again, we're going to go through partial fraction decomposition. And if you look, this is going to be a quadratic factor squared, so repeated quadratic factors. So quadratic factor repeated means we have to account for each portion. So there's x squared plus 9, there's also x squared plus 9 squared. And then because both of these are quadratic factors, we have to make an adjustment with the numerator as ax plus b and cx plus d. Okay, so same idea as number 9. We're going to multiply the entire equation through with the common denominator, which is x squared plus 9 squared. So if I distribute this through and see what's left, this expression, the denominator, will cancel out perfectly, leaving out which is x squared minus x plus 9. If I distribute the x squared plus 9 through the first fraction here, I'm left with ax plus b times x squared plus 9. And then here, the third expression, the numerator and denominator will cancel out perfectly, leaving out with just cx plus d. So let's see if we can figure out a, b, c, and d by using some easy values for x. And so an easy value that we can use for x will be 0. Okay, so if I plug in 0 for all the x's, let's see here. If I plug in 0 for all the x's, looks like everything will cancel out, leaving us with just let's see. So this will go away as 0, so I'm left with 9 times b. This will go away, plus d is equal to 9, so this will be one equation. Another thing that I can do is I can replace each of the x's with 1s, and if I do that, I'll get 9a plus c is equal to -1, so that's another equation. And from here we can figure out that c is equal to -1 and d is equal to 0, and also we also can figure out that a is 0 and b is equal to 1. And then once we have that, we can have our equation a lot easier to deal with. 1 over x squared plus 9, which is our tangent rule. -x over x squared plus 9 squared, that's a u substitution problem. So go through arctangent to figure out this 1/3 arctangent x over 3. Go through u substitution. Let the u value be x squared plus 9. Find the indefinite integral, and we're left with 1 over 2 x squared plus 9 plus c. Okay, 8.7 and 8.8. All right, these are problems that involve limits. So we can think about stepping through a limits checklist. So if we see a real number, we want to just go ahead and plug in, and if we see indeterminate forms such as 0 over 0, we can further evaluate using L'Hopital's rule. If the limits approach infinity, we can compare degrees between numerator and denominator. And if it's 0 over 0 or infinity over infinity, we can, again, apply L'Hopital's rule. All right, so 11, we have limit as x approaches infinity of x cubed over e to the x over 2. Now, if I plug infinity in for the x into numerator and denominator, I'm getting infinity over infinity. So this is an appropriate indeterminate form for us to apply L'Hopital's rule. So L'Hopital's rule, we're going to find the derivative of the numerator. Separately, find the derivative of the denominator. So x cubed becomes 3x squared. E to the x over 2 is, the derivative for e to the u is e to the u times u prime. So u prime is 1/2. Okay, so now we can reapply our, reevaluate the limit. So if we do that, we're again going to get infinity over infinity. So let's find the derivative again. 3x squared becomes 6x. 1/2 e to the x over 2 becomes 1/4 e to the x over 2. Now if I plug infinity in for, again, infinity over infinity, so replace the x with 0. Find the derivative of each of the terms here. So 6x becomes 6. We get 1/8 e to the x over 2. Now if I plug infinity in for the remaining expression, I get 6 over infinity, which is equal to 0. All right, number 12. We have limit as x approaches 0 from the right side of 0 of 1 plus x raised to the 1 over x. Now, if we have a variable expression raised to another variable expression, we want to try and involve natural logs. So first off, I'm going to rewrite. I'm going to set this entire limit expression equal to y. And now I'm going to try and involve natural logs, because when I involve natural logs, I can bring that 1 over x down. So I'm going to take the natural log of both sides, bring over the 1 over x down. Now, if this is essentially going to be in the denominator, so I'm left with natural log 1 plus x over x. If I'm approaching 0 from the right side of 0, the numerator will go to infinity. The denominator will also go to 0. Well, it's actually 0 over 0. So if we get 0 over 0, we know we can go through L'Hopital's rule. So the derivative of the numerator gives us u prime over u, which is 1 over 1 plus x. The derivative of x is going to be 1. Reevaluate. Plug in 0 in for x, and we're left with 1 over 1, which is 1. But that's not quite finished yet, because right now we've just found the limit of this expression. This is still set equal to natural log of y. So natural log of y is equal to 1. If I solve for y, converting it to exponential form, I get y is equal to e to the first power. Okay. Last two here, 8.8. These are dealing with improper integrals. So sometimes improper integrals are at the endpoints or at the boundaries, external boundaries. But in this case, if you look at 13, the boundary where this expression is undefined, it's going to be at 1, which falls between 0 and 2. Because if you look at 1, when x is 1, the denominator will be 0, so there's a vertical asymptote there, which means that there's an internal point of internal point that is undefined. So we're going to have to, of discontinuity, so we're going to have to split this up into two separate integrals, from 0 to 1 and then from 1 to 2, and we want to split it at the point of discontinuity. So from this side, we're going to think of, we know it can never be equal to 1, so we're going to let that be the b value, and then pull that out as limit as b approaches 1 from the left side of 1. And this will be from the right side of 1, as b approaches 1 from the right side of 1. Okay, so we're going to go through use substitution here. For the first expression, we're left with 2u to the negative 2/3, going through power rule with 2u to the 1/3 over 1/3. And then we can evaluate the limit as b approaches 1 from the left side of 1 by plugging in b in for the x value. So we're left with 0 minus negative 6. And then on the right side here, if we go through use substitution, evaluate the upper and lower bound, plug in 2, then plug in b, we get 6 minus 0. So we get 6 plus 6, which is equal to 12. Okay, 14. We see improper integral, but this time the improper integral is existing at the outer upper bound here. So if we look at this pairing between x squared and natural log of x, looks like this is going to be having to go through integration by parts. So integration by parts is uv minus integral of v du. Anytime we have natural log involved that's paired up with another function, our u value is always natural log. So u value is natural log of x, derivative is 1 over x. dv is therefore x squared, so the integral v is x cubed over 3. So we go through and replace everything that we can replace. And we still have to take care of this integral here. So integral of negative 1/3 x squared. We have to evaluate this between our upper and lower bound. So now plug in upper bound of b, followed by lower bound of 1, and now replace all the b values with infinity, and we see this approaches infinity, this is also infinity, and this is 0, so we have infinity minus infinity, which will stay as divergent infinity. So we know that this integral does not converge, but rather diverges.